Good day to everyone. Okay, from previous class or previous lesson, we already go through our speed control by adjusting armature voltage. So when we adjust this armature voltage, what would happen to our motor speed here? And it can be seen that it will affect the characteristic of the speed versus torque by means of it will give you a parallel characteristic of each slope at a different initial speed. Okay, so now let's proceed with example 5 to enhance your understanding. Okay, for example 5, it says that for 20% increase in the armature voltage, so this is your VA, calculate the percentage of change in the no load speed. Okay, assume that the load torque is unchanged. So if we write back the speed versus torque, speed torque equations. So we have this one, speed VT over kV minus RA TD, speed versus torque, kV square, and this one is equals to no load speed minus the speed drop. Okay, and let us assume that omega naught 1 flux 1 and VA1 is the variable for initial condition. Okay, and for omega naught 2, flux 2 and VA2 is the variable for the required condition. Okay, for 20% increment of VA, armature voltage. Okay, so you can assign back, since we are tackling the no load speed, this one, the no load speed changes. Okay, the question is actually wanted you to look on the changes in no load speed. Okay, no load speed if we wanted to increase this VA by 20%. So itu the requirement. Dia maksudnya jika kita increase VA, terminal voltage tu sebanyak 20%, speed tu akan berubah. How much does there's changes on the no load speed. No load speed meaning this one. Okay, so how much it's changed. So when we are talking about no load speed, we just tackling only this first term of the equation. Okay, for now let's write back the related equation. So this omega naught 1 equals to VT over kV, or VA1 over kV. Since this is a separately excited, so we know that the VT is equal to VA, right? Okay, so this is your VT and it is the same parameter for your VA. So it's sama lah bendanya. Okay, and then after you increase the armature voltage, what happened to the load speed? It will become the new value. So this is the new value of no load speed here. So you have new value of your VA, armature voltage, since you increase it by 20%, and you have your kV. Okay, so now let's check apa yang berubah. What have been changed after you change this VA. Okay, first your VA1 is the initial value. So your VA1 is 100%, okay, or 100 over 100, so no changes. So VA equals to 1, and your VA1 here, and for your VA2 is 20% increase from VA1 here. Okay, so VA2 is 20% increase from VA1. Okay, this is your VA1. So now how much is your VA2? VA2 is 120% of VA1. or it's 120 over 100 from VA1, which give you 1.2 of VA1. Okay, next, since the question says that the load torque is unchanged, okay, so when the no load torque is unchanged, we can assume that the field is keep constant. Okay, field this one, this one, this one, this one, and this one. So for both initial state and the changes, the requirement of the changes of VA, okay, walaupun you ubah VA, but the flux is still constant. So when it's constant, meaning it's hold one value. So together you can cancel this one and this one. Okay, and in the same time you can also make the ratio between speed 1 over the no load speed 1 and no load speed 2. Okay, kalau we write back the equation, which is VA1 over KV divide by VA2 over KV, and if we flip this part, since it's a division divider, VA1 over KV multiply with KV over VA2, and we already know that this one is a fixed value. Okay, so you can cancel the flux between original or initial state and the changes, the state after 20% changes. Okay, so now what left on your equation is VA1 over VA2. Okay, and from here VA2 is 1.2 VA1. Okay, so if I write back here, the no load speed 1 over no load speed 2 equals to VA1 over VA2, and if you fill up this VA2, VA1 over 1.2 VA1, you can cancel this VA1 since it hold the same value. You will have 1.2 omega naught 1 with omega naught 2. Okay, so what does it mean? It's mean that when we change the armature voltage, or we increase the armature voltage by 20%, what happened to the no load speed? It will also increase by 20%. Okay, okay, how about the second terms of the equation, is this one, ataupun the no load, the speed drop, the speed drop of the motor. Okay, is there any changes? If you can see here, when we change this one, okay, it's only affect the first term, which is the no load speed. Okay, so when this 20% increment of armature voltage, it's only affect the no load speed, and how much the no load speed have been affected is when we add up 20% increment on the VA2 or the armature voltage, we can expect that the no load speed will also increase by 20%. Okay, but in the same time we can see that there's no parameter involved on the speed drop, parameter of armature voltage involved in the speed drop. Therefore we can conclude that the no load speed changes will not affect the speed drop. Therefore the speed drop will remain unchanged the motor. Okay, but bear in mind, for this method we can only use by means of the flux, below flux, and the torque load is fixed or no changes. Okay, so bila flux dia tak berubah, load torque tak berubah, TL dia tak berubah, kan kita ada, we have this graph. Okay, this one. Okay, the load torque, this one usually the load torque or the load current. Okay, no changes, we can use this ratio method. Okay, then for example 5, okay, you can also refer solution provided on the slide. Okay, okay, now we look on another method of controlling our motor speed here. Okay, is by adjusting the field voltage. Kalau previously we adjusting this one. Okay, imagine that this is your full circuit. You have your VA here, and you give a variant value of your VA here. And what happened if we don't want to adjust? You might want to keep this value fixed. This value fixed, but we wanted to adjust this value, the field voltage. So what happened to the characteristic of your speed versus torque of your DC motor? You can see that the slope is not in parallel anymore, but it still give you the no load speed reduction. Okay, and together with the no load speed reduction, you will have also reduced the motor speed here. So this is your motor speed 3, motor speed 1, this point, motor speed 2, and motor speed 1. Okay, if we put some value here, let's say this VF1 is like 120, 180. Okay, bigger, smaller, right? So we can see that this one is 80, this one is 100 volt, and VF1 is 120 volt. Okay, the larger the field voltage, the smaller or the more reduce your motor speed and the no load speed. Yet it also give you different speed drop, the different slope. Yeah. Okay, itu yang initial expectation that we can see from the graph. Okay. And also you can read from here, adjustable voltage source is connected to field winding. Okay, yang ni fixed, VA is fixed. If field voltage is reduced, the field current, consequently the field flux are reduced. Okay, because it affected the field current, it will reduce and affected the BMF of the motor. Okay, when the field flux is reduced, the no load speed is increased. Okay, even though you reduce, tadi saya cakap the larger, right? Tapi kalau you baca from aspect of field flux, okay, when the field flux is reduced, meaning that you reduce from here to here, from 120 to 100 to 80, reduce lah, kurang. Okay, it reduce, the no load speed will increase in inverse proportion to the flux, and the speed drop is also increased. Baliklah definasi yang sama, ataupun the same statement, but you explain it differently. Kalau tadi my early explanation is I increase the VF from this point to here, the VF is increased. But if you tell from here to here, the VF is reduced. So when your VF reduce, what happen? Your speed will increase. Tengok speed dia makin lama makin naik. Okay. The characteristic shows that because of the changes in speed drop, the lines are not parallel anymore. Okay, and we can see that from this equation also. There's no VF here. However, changes of field voltage will give effect on this one, flux. Okay, and flux will give effect on the initial speed and the speed drop. Sebab tu speednya berubah, the changes on the speed and as well as the speed drop here. The slope is also different from one point to another. Okay, let's go to example 6. Okay, by the way, before we proceed to example 6, take a look at this example. Okay, this example actually it doesn't give you any parameter value for your motor, right? So you can see that even though you only have basic or no value, you have only the parameter, but you can expect what is the changes would happen to your DC motor if you tackle the main parameter value. Okay, you just need to know this one. Just need to know the equation, the right equation. and what is the circuit. Okay, whether it is a series, separately excited, or shunt. So different circuit will give different effect, but it share the same characteristic of the DC motor behavior. Okay, now let's go for example 6. Just extending the example 5 question, it says that for 20% increment in the armature voltage, previously for example 5, calculate the percentage change in the no load speed, right? But for example 6, it's extend the requirement, assume that the the load torque is unchanged. Repeat this calculation for a 20% reduction in the field flux. Therefore, let's say flux 1 is the initial state. Flux 1, initial condition, and you have flux 2 is the 20% reduction in the field flux. Therefore 20% reduction, so 100 minus 20% from flux 1. Okay, so your flux 2 is actually 80% of flux 1, or you might write it as well as 0.8 from flux 1. Okay, let's write up the speed torque equation. We have your Vt over flux or Kv, Ra Td, since the load torque, so kita letak T lah, torque Ra Td Kv square. Okay, and it's involve the 20% reduction. You can see that from the equation, reduction in here, it's involve both first and second term of the equation, right? And this first term, we know that it is the the no load speed and the speed drop. Okay, so we can look on effect of this reduction of flux from no load speed and also from the speed drop. Okay, no load speed effect, omega naught. Okay, so for no load speed effect, we know that this is your no load speed, this is the equation. So no load speed equals to Vt over Kv. Okay, since load torque is unchanged, so we can also use the ratio method. We have no load speed 1 over no load speed 2. So VA1, I change this terminal voltage to VA1 because we still assuming the motor that we are analyzing is a separately excited type. Okay, so VA1 over KV1 and divide by VA2 over KV2. Okay, we know that K is the voltage constant of the motor, and we have new value of flux, so we can change the flux. And for this example, we need to bear in mind that this one is changed. Okay, because when you change this parameter, you need to assume that your Vt is fixed as well as the torque as well as the armature resistance. There's no changes, we only change the flux, and we need to see what is the effect of these changes towards your motor speed, and motor speed involve the initial load speed and the speed drop. Okay, so now from this one you can fill up. We know that this Vt or Va is fixed. Okay, so you can cancel this part and you can rewrite back the equation. So it's Kv2 over Kv1, and you can also cancel this K, which leave you no load speed 1 over no load speed 2 is flux 2 over flux 1. And flux 2 here equals to 0.8 flux 1. So 0.8 flux 1 over flux 1. Okay, and we can cancel this part, which give you, I bring this omega naught 2 to the right. So omega naught 1 over 0.8 equals to omega naught 2. So 1 here divided with 0.8, it will give you 1.05 omega naught 1 with omega naught 2. So what does it mean? It means that it's 1.25, right? So it means that it's a 25% increment from omega naught 1. So 25% increment from no load speed. Okay, you can also say that the new no load speed will increase 25% from initial no load speed. Okay, so the new no load speed is this one. The initial no load speed is this one, omega naught 1. Okay, this one is the effect of no load speed. Now let us see the effect of speed drop pula. So for speed, apologize for my handwriting. So for speed drop effect, okay, delta omega. So the speed drop effect involves the second term of the equation. Delta omega equals to RA TD over kV square. Bracket kV square. Okay, for this one, we have initial condition RATD over kV square, and since its torque is fixed, and also as well as the armature resistance, we can apply the ratio method. So this one divide with, okay, the no load the speed drop 2 with RATD over kV square. Oh, sorry, this kV square is written incorrectly. So kV square, careful kV square, and this one is kV1 here, and this one is kV2. Tak nampak, kV2, kV1. Okay, and rearrange to make our calculation or analysis easier for you. So RATD over kV1 square, kV2 square, RATD. Okay, remember that this torque and armature is fixed, can cancel out, and you can cancel also this K, which give you flux 2 square over flux 1 square. Okay, so summarize by the equation. Flux 2 square over flux 1 square. Okay, and okay, or you might also can write it like this, flux 2 over flux 1 square. Okay, from, sorry, tolak sikit. Okay, from this equation, okay, you can assign this value for flux 2 0.8 flux 1 over flux 1 square. Solve the equation or simplify the equation. Can cancel this one, which give you 0.64, right? Okay, and since we wanted to see the effect of the speed drop, so we wanted to see this omega delta omega 2. So bring this one to the right side of your equation, which give you 0.64 equals to delta omega 2, and solve this part. This one is 1 over 0.64. Dapat berapa? You will get 1.56 equals to delta omega 2. Okay, so for 1.56, what does it mean? It means it is a 56% increment of speed drop. From initial condition. Okay, the longer version is, if we reduce the speed by 20%, what happened? Then, sorry, if we reduce the flux by 20% from the original flux, what happened? The rest of the flux is now is 80%. Okay, with this 80% flux from original or from initial condition, you reduce the flux, but you increase this flux reduction will increase the speed drop by 56%. Nampak tak, dia macam tak drastically increment. You reduce sikit je 20%, tapi dia naik sampai 56% of speed drop. Okay, when the speed drop increase, dia punya no load speed pun increase, which means that when this part is increased together with this part, motor speed will also increase lah. But on the initial setting, you sebenarnya reduce flux. Okay, flux reduction will increase your speed. Okay. Okay, from both example 5 and example 6, what can you conclude is that from example 5, example 6, okay, so from example 5, what happened? You 25% increment of VA, okay, and what happened is you increase 20% also of the no load speed. Okay, however, for example 6, for this example, we reduce 20% reduction of flux. Okay, but we have two parameter changes, which is 25 on this one, 25% increment of no load speed and 56% increment of speed drop. Okay, that's the conclusion. Okay, and you can see that if we relate this finding with the equation, we can see that dependency of motor speed with the flux. Okay, which apa dia dependency dia tu? The no load speed. Okay, the no load speed is inversely proportional to the square of the flux. Okay, and we can see that even when we reduce the flux, it will give you huge difference on the motor speed. And what does it mean? It means that your motor speed will be more sensitive to the flux variation rather than armature voltage. Sebab macam armature voltage ni, tengok you reduce 20%, you dapat 20%. So dia linear relationship. But untuk example 6, dia not really straightforward punya speed control. Sebab you reduce sikit tapi you increase banyak. Okay. You can also read more theory on the slide. Okay. Ini pun sama. Already mentioned to you. 20% changes in armature voltage is 20% in no load speed and 0 changes in speed drop. But when you change 20% in field flux, it have both effect in no load speed and speed drop. Okay, next. Apa ni? Okay, by adjusting field voltage, when motor is controlled by adjusting field current, you need to aware that field voltage must not exceed the absolute maximum rating. Sebab let's say for this separately excited DC motor, we have both supply for terminal or armature and field. But if you adjust this one, you must not exceed the absolute maximum rating of the field voltage, because the speed will be more in uncontrollable condition. Okay, since DC motor are relatively sensitive to variation in field voltage because it involves flux, okay, large reduction in field current may result in excessive speed. Kita tak nak, sebab bila too much ataupun untuk application yang not too okay, it will damage your operational, or it may affect your operational of the load. Okay, and because armature current is inversely proportional to the field flux, reduction of fields result in increment of armature current by assuming that the load torque is unchanged. Okay, now let's take a look on what happened if we add a series field resistance. Tadi previously we adjust this one, okay, but now we make this one fixed as well as your VA also fixed, but we adding series field resistance, this one on your circuit. What happened? Okay, we can see this effect on example 7. Okay, for example 7, it says that for 150 volt DC shunt motor drive a constant torque load. So your TL is constant. This is your motor speed 1200. The armature and field resistance are 2 and 150 ohm. So I just draw the circuit directly. RPM. Armature and field resistance 150. Armature is 2 and you have field resistance 150 ohm, and the motor draws a line current of 10 ampere. 10 ampere. Assume that a resistance is added in the field circuit to reduce the field current by 20%. So it's added one more RF or RL lah, additional resistance. Calculate the armature current, motor speed and value of added resistance and extra field losses. We need to find this one, armature current. So IA, need to find motor speed, need to find value of added resistance, and extra field losses. So extra field losses referring to additional resistance there. So it's PRX. S2 RX. Okay. Extra field losses, bukan field losses. Field losses will involve RX and RF here. This one RF, and this one is your RA. Okay, so but since the question only asking you to calculate the extra field losses, meaning this one lah. When you add more resistance, you get extra losses for the circuit or for the motor operation. So now, where should we start? Okay, we started from before we insert the RF. Okay, so check from here. Before insert RF, what happened? We have IA1 equals to IM minus IF. Where do we get this? We get this from here. So this is your IA, this is your IF, and this is your IM. Your IM is equal to 10 ampere. Okay, so it's 10 minus IF. So IF, let's say I didn't add this. Assume that we have only field resistance here before insert RF. Okay, so your IF, okay, this point and this point is obtained from one source. So this is your VA. So its IF is equal to RF. IF I sama dengan V over R. VF over RF. Since this is a DC shunt motor drive, so your VF is equal to your VA over RF, and it's also equal to your V terminal over RF. So simple je. So IF is your VA. VA is 150 volt, so it's 150 over RF 150 ohm, which give you this one is 1, kan? So now you have your 9 ampere for armature current. Okay, step 2. Since the load torque is constant, we can say that load torque 1 equals to load torque 2 equals to load torque. Sama, dia tak berubah. It's the same value. So dia tak payah letak TL1 or TL2 lah. You letak TL saja. So easier for you to analyze your calculation. Okay, so now you have torque equals to KVIA, right? Okay, and since it's constant, you can say that KV1 IA1, KV2 IA2. Okay, and this K is the motor constant. You can cancel out because it is the same construction of the motor. We are talking the same motor. And now, okay, since we are adding the resistance in the field circuit, we must make one more assumption, which is assume that flux is linear to IF. Yelah, sebab flux kan it's in dalam field circuit, kan? It's inside your field circuit, so it's linear. When flux changes, field current is also change. Okay, so now you have another assumption and another equation to consider, which is from this one. Okay, so I write it back here. Flux 1 IA1 equals to flux 2 IA2, and since it's the relationship is linear, you can say that this one is field current 1 IA1 equals to field current 2 IA2. 1 and 2, what's the difference? Field current 1 maksud dia no added resistance on field circuit or initial condition. For IF2 with RF on field circuit. Okay, remember, okay? Okay, now back to the questions, because the question said that assume that a resistance is added in the field circuit. What is the effect? It will reduce the field circuit, the field current by 20%. So now when we add the resistance, we have new, when we add the resistance, we have new IF2. So what is this new IF2 effect? IF2 is 100 minus 20%. Okay, question said what? Field current, reduce field current by 20%. Okay, so from the original condition, field current will be reduced by 20%, which will give you new field current. Okay, so now new field current is 80% from original state of field current. Okay, so now with this 80%, it will give you 0.8 IF1. Okay, IF2. Okay, now let's take a look on this equation back. Okay, fill up this IF2. Okay, so now IF1 IA1 equals to IF2. I write back this one, IF2 IA2, and we have this, your IF2 is 0.8 IF1 IA2. Okay, so take a look on the equation. Apa yang kita boleh, what can we simplify from the equation? We have this one, we have this one. We know that this IA1 calculated from here is 9 ampere. So put 9 ampere on the equation. So 9 equals to 0.8 IA2. Okay, now you will have your IA2 with 9 over 0.8 equals to 11.25 ampere for your IA2. Okay, now let's move forward. Okay, next we need to calculate the speed, right? Okay, so number one here, number 2 and number 3. To calculate speed of your motor, we know that we have another equation for your motor, which is EA equals to kV omega. Okay, and we also can have this kV, Kirchhoff voltage, KVL Kirchhoff voltage law for this EA. This one is your EA, positive negative, your RA positive negative, your VA positive negative. So this is your loop. Okay, from this loop you can write down the equation for which involve V and IA1. So V IA1 RA, which V VA lah. Okay, and when we add the additional resistance here, okay, what happened? From step number 2, we know that we have new armature current. Okay, so we have new EA, EA1, EA2, kV omega 2, kV1, kV2, omega 1, omega 2, with the same VA, since we not change the armature voltage, but we have new IA2 RA. Okay, we can say that when we add the RF, V2 tak berubah. Okay, the only change is the flux and motor speed. Okay, since the load torque is constant. Okay, you can make the ratio between EA1 and EA2. You can expand the equation. Okay, so it's Kv1 omega 1 divided with Kv2 omega 2. Okay, equals to this one, VA minus IA1 RA over VA minus IA2 RA. Okay, okay, since we are going to calculate the motor speed in RPM, so we can simply replace this omega with N. Okay, so it's flux 1 N1 over flux 2 N2, so equals to V minus IA1 RA plus V minus IA2 RA. Okay, careful okay. Focus. Okay, since tadi earlier we said that flux is proportionally with field current. Okay, and we know that this one, okay, flux is proportional to field current, and we know that IF2 is equal to 0.8 IF1. Okay, fill up here. We will use this term in here. Okay, so fill up the IF2 or flux 2. Okay, okay, we can write some note here. Since flux proportional to IF, okay, we can see from here or from here, so IF2 equals to 0.8 IF1. Since this equation is using the flux terms, okay, so kita boleh replace terus. So flux 2 equals to 0.8 flux 1. Okay, and we need to use this one to fill up here. Okay, so now flux 1 N1, flux 2 is 0.8 flux 1, and we can directly fill up this value. So we know that your V is 150. We have your 9 ampere for IA1, and we have 11.25 ampere for IA2. So you can just straight away fill up the parameter value. So it's 150 minus 9 times 2 over 150 minus 11.25 is IA2 times 2 ohm. Okay, settle this one. Oh, I forgot to put this one, N2. Okay, and one more thing, this N1 is what? It's this one, initial condition for motor speed. So it's 1200 RPM. N in RPM. Okay, since we can cancel this one and this one, you can have your N2 motor speed. Rearrange the equation. You can have your N2 with 1448.86 RPM. Okay, so if you interested on knowing the changes in speed, we can extend the analysis with, for when N1 is 1200 with reduction of flux, 20% of flux reduction, so we can find the percentage percentage changes equals to N1 minus N2 over N1 times 100%. So it's 1200 minus 1448.86 over 1200 100%. Okay, since it's increase, so we know that it's increment, so we can just write out the 248.8 ignore the negative because we already know that the speed is increased from the initial speed. Okay, 100%, and it gives you 20.7% speed increment. Okay, next we have the motor speed. Now we need to find the additional resistance. Okay, so number 4, value of additional resistance. How can we find it? Just take a look on this part. Okay, we know that VF is here, this point. This is your VF. Okay, equals to what? IF2 RF plus RF. Okay, VF, this point, same point here, same point here. So your VF is 150 volt. IF2, what is your IF2? IF2 is this one. 0.8 IF1. Okay, IF2 is 0.8 IF1, and the RF is the one that we need to find, and your RF is 150. Okay, what is your RF? IF1 ini 1 ampere, right? So 0.81 RF plus 150. Okay, rearrange the equation and you can find your RF, which is 37.5 ohm. Okay, that's your value of additional resistance on the field circuit. Next, we need to find the extra losses. So extra losses due to this RF. Okay, so it's P RF equals to current mana yang lalu? The current that flowing through this RF is IF2. So it's IF2 square RF. So what is your IF2? IF2 is 0.8 IF1, which is 0.8 times 1. So your IF2 is actually 0.8 square times this one, 37.5. Okay. So your additional losses is 24 watts. Okay. How about the field losses? So field losses will involve RF and RF. So if you wanted to calculate the field losses, I tambah from the original question lah. So the field losses is P F, which is IF2 square RF plus RF. So it's 0.8 square 24, sorry, RF here 37.5 plus RF 150. Okay, so it's 120 watts for the total field losses that involve in field circuits. Okay, so that's all for example 7. What is, okay, this is Raya quiz and it stacks you 10 marks. Okay, please write up this the answer for this quiz on a piece of paper so that we can check on next face-to-face classes. Okay, refer to the previous example 4. We already done it on last week, and example 7 that we already done it recently. Compare the losses when adding additional resistance on armature circuit versus on a field circuit. Okay, assume both example 4 and 7 have same rotational losses of 100 watts. Conclude your finding. What can you compare between example 4 and example 7 if you add resistance on additional on armature or on a field circuit, and provide a comparative table to support your findings. So 10 marks is a lot, So try to give as much information or as much comparative analysis as possible so that you can gain 10 marks. This one is not on the recent or on the uploaded slide. It's only on a video, and I will upload this question in a different file on your e-learning later. Okay guys, thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh. And don't forget to scan your attendance for today's lesson. Thank you.